Thanks, Dean of the course, for the introduction, and of course, Vice President Steiner for this engaging opportunity. I'm going to talk to you today about 4 historically important mathematical models that reflect a biological phenomenon. And then I'm going to continue on with the work that I do in terms of collaboration involving the migration of clustered cells in Drosophila fruit fly. So in 1926, Vito Volterra was an Italian mathematician, wrote a paper with his son-in-law, Umberto D'Ancona. And Umberto is a marine biologist, and he noticed in a local fish market that there were periodic amounts of predatory fish versus prey fish in the market. And so he was wondering, well, what might this cause this situation? And so he got together with his father-in-law, and they decided to, using some of the early work from Lotka, to write down mathematical models that represented the biological phenomenon, and were able to write down equations that captured some of the behavior. And lo and behold, these equations captured this periodic behavior of the prey and the predator. Right? And so once this abstraction was derived, then you can apply this to a variety of different scenarios. So land animals, insects, a variety of different contexts. Right? And so, in fact, most of the work on food webs and interspecies interactions are derived from this early model. In 1927, Anderson McKendrick, who is a biochemist but interested in mathematical phenomenon, got together with William Kermack in deciding to study the disease progression, and they came up with the susceptible, infected, and recovered model of disease. And so in this situation, we have sort of susceptible population interacting with infected populations at, say, a rate beta. And then you have the recovery of infected populations at, say, gamma. And so the ratio of this infection to recovery represents an R0. And with an R0 value that is much greater than 1, then you get a highly infectious situation. In the spring of 2020, I was beginning to teach my biomath class. And the first day of class, I decided to put up a slide that represented an emerging disease that was coming out of Wuhan. They're calling it COVID-19. A few hundred examples, one over there in Seattle popping up. Thought it'd be a good thing to keep an eye on. So it goes without saying that mathematical representations of disease spread are extremely important in today's world. 1952, Alan Hodgkin and Andrew Huxley, both physician biophysicists, got together and studied the potential in nerve cells. And so they were able to find that a mathematical expression to capture this motion of potential through the nerve cell, and importantly, they were able to capture the gating of ion channels. So ions would be able to flow through into the cell and depolarize the neuron, and then potassium gates would open and potassium ions would flow out and repolarize the neuron. So combined, they would form an action potential. This allows for the potential to go along axons and for information to travel along cells, right? So, they won the Nobel Prize for Medicine in 1963, and forms the basis of basically all of the interactions in brain science, and even artificial intelligence is oriented in those modeling early days. So in 1970, Evelyn Keller and Lee Siegel, Evelyn Keller is a physiologist and Lee Siegel is a mathematician, they decided to look at amoeboid movement, and amoeboid movement in response to chemical signals. And so what they were able to find was they had a population of chemical secreted by cells, say V, and then the cells themselves would respond to this chemical, and they would move up chemical gradients. Right? And so what they would find then you would find these fruiting bodies in response to these chemical gradients. And so this is a mathematical framework that captures a lot of interesting work in development, in wound healing, in cancer metastasis, and it actually feeds into the collaborative work that I began in the last few years. So in 2008, I joined UMBC, And shortly thereafter, we got a training grant to study, to help undergraduates be trained at the interdisciplinary interface of mathematics and biology. And in this process, I was able to meet fellow newbie, Michelle Stars-Gaiano, developmental biologist who had a fantastic model system, still has the fantastic model system, of the Drosophila fruit fly egg chamber. And in this process of at certain stages in this development, you find a group of cells that cluster at the anterior end. They make their way through the nurse cells to the oocyte on the other end and continue the developmental process. Now, in the process of moving, they sense these chemicals that are throughout the system, much like you might sense the aroma from a bakery with your nose and follow it to that space. So lots of questions arise with this movie. Biological and even mathematical questions can arise with this. So one of them was, okay, how do these cells originate at the anterior end? And so Michelle had a graduate student, Lathina Manning, who was able to take this, this football-shaped egg chamber and basically turn it on its end and look at the top down to see sort of the activation pattern of the cells. And with the secretion starting at the middle, you might initially think that, well, sort of the local, the closest neighbors might be the ones that activate. And there are some of that, but there are quite a few different structures as well. Some asymmetries, some gaps. The question is, well, maybe why is that happening? Well, so we developed a mathematical model to sort of test the idea that maybe underneath this layer, there's a microenvironment. There's a sort of a biasing that happens with the signal that then leads to these different activation patterns. And lo and behold, with this mathematical model, we were able to show and reproduce all of these different activation patterns that the experimentalists were able to see, right, by changing a couple of different geometric features of the microenvironment. So another question might be, okay, how can we represent the migration of the cluster itself? Well, so we take advantage of agent-based modeling in this particular case, and we take these agents and we put in some basic forces, some repulsion, some adhesion between the agents. And then we say, okay, so maybe there's a little stochastic force, and maybe most importantly, we have this response to chemoattractants, right? And so we put these agents together in both the clusters and in larger nurse cells, and we are able to show that, indeed, we can get, with just these basic forces, a migration through the egg chamber, right? So adhesion over adhesion, fist over fist, like a rock climber making its way through the rocks, right? So along this pathway, again, there's this chemoattractant that's involved, but the environment is very challenging in the sense that experiments are very difficult to see the distribution of the chemicals in this context. And so nextly, we took a look at this main axis, this main pathway of migration, and we hypothesized that, okay, there's some gaps in between the nurse cells along this pathway. And we were able to sort of suggest that, well, the trajectory of the cluster as it makes its way through with varied speeds is due to this underlying geometric formation. And so we created a model that captured this, and we're indeed able to show that there's variation in speed. Right? But then once you have this model, you want to test it, right? You want to test the prediction. So we increase the chemoattractant, and we increase the distribution of chemoattractant in that space, and we show that, well, the cluster actually counterintuitively slows down in that process. Well, then we say, okay, well, what happens if we then open that gap back up? If we increase the gap and we decrease the distribution a little bit, well, we in fact recreate the speed of the original situation. And so we can do this with the model. That's great. We can do that with the model. But can we do that with the experiment? And indeed, we were able to reproduce that experiment by overexpressing chemoattractant in the native egg chamber, and also do a mutation where we actually increase the space between nurse cells. And it reproduces the same sort of effect. We have a slowing down of the migration, followed by a rescue with the mutation. So lastly, most recently, we've been looking at a phase field model framework to look at how our cells are interacting. And so we have an individual cell that acts as a phase. So we have a 1 when we're inside the phase. We're 0 outside of the phase. And what it allows us to do is that have multiple phases interacting, multiple cells, and it puts us into a partial differential equation framework, which allows us to attack this problem a little more efficiently. But we need an additional term in our migration, which is this a brand new novel term, tangential interface migration force, which is able to capture this rock climbing effect of clusters of cells making their way through nurse cells. This model then provides us with a framework to be able to study more migration questions, including multiple chemoattractants at the same time. Right? So the historical examples that I shared, the recent work that we've been doing, are all due to interdisciplinary collaboration. Right? And so I'm actually super excited to say that we've just been, with the donation from the CNMS Dean to start it up, we're starting a Center for Integrated Mathematical and Biological Sciences Research and Education. So I'm happy to talk about anybody about that afterwards. Thank you.